Hello, today we will look at some applications of ordinary differential equations, namely ODEs of order 1, because we already looked at them a little bit. Let's start with something that you already heard, most likely. People sometimes say that the more money you have, the more money you make. So let's have a look at it, and we will use Y to denote the amount of money that you have. So that's our wealth. And of course it changes in time, most likely. So Y is a function of time. The more money you have, the more money you make. Okay, what does it mean, making money? Well, when you make money, it means that your wealth increases. So the money you make actually refers to the increase of your function, or in other words, the rate of increase, in fact, and that's the derivative. So the more money you make translates mathematically into the derivative is larger. So the more money you have, the larger the derivative of your money. Okay, so far so good. The more money you have, the larger the derivative. Well, there should be some correspondence. Now, which one? That's a good question. Let's try something very simple. Proportion. There is some proportional constant times how much money you have. Yeah, this could work. The more money you have, the more money you make. That sounds reasonable. Now, what we just did, we created a mathematical model for your wealth, for your money. This is a mathematical equation, and when you write something like that, it creates a virtual mathematical world. So mathematicians very often create artificial worlds with its own rules, which are usually given by some formulas, and then they try to investigate this world, hoping that they will learn some insight into whatever things they are modeling. Here we are modeling money, so when we look at this model using mathematical tools, we will perhaps get some insight into money, which is a nice thing, of course. So let's have a look at this model. That's an ordinary differential equation, definitely. It's of order 1, definitely, and it's separable. That's a good news. Let's separate. We want to divide by Y, definitely. So here is a side note. Y equal to 0, that's a stationary solution. Having this out of the way, we should also look at restrictions. Do I see any restriction? The answer is no. So I can expect solutions everywhere with a bit of luck. Here we go. We separate. We divide by Y, and I visualize this as dy over d, let's say dt, because it's time. So dy is left here, and I move dt to the right. Now I attach integral signs, and we are happy. We have a nice separation, and we keep going. I integrate. I integrate. I look at it and say, well, we saw this one before. That's the problem or the differential equation with logarithms. So we know that we should take the exponential of both sides. Now we replace the absolute value with plus minus and put it here, but then we multiply the whole equation by plus or by minus and it moves here. So y is plus or minus e to c times e to rt. And finally, we will introduce a new constant here. Yt is equal to d times e to rt. And because this is an applied problem, we will use the applied condition. We start at time 0 and see what's happening with our money, or whatever else. We will get to it soon. Now, we commented it before, so let me just remind you that this constant over here, this little object, can never be 0. But if we put 0 for d, we will actually incorporate the stationary solution. So this is really the general solution. Very nice differential equation. Very simple. And the outcome is an exponential based on this constant r. That's the proportional constant. So this all nicely fits. Now, it actually fits even better. Initial condition. Let's see that we know what's happening at time 0, because we just count our money. No problem there. Now, when we substitute 0 for time, this becomes 1, and it means that d should be actually y0. That's wonderful. We are actually able to provide a nice formula if you know the initial data, which means how much you have at the start and what is the proportional constant, then you can immediately write down the solution. And that's the overall picture that we want to see. We have a differential equation. We have an initial condition. And from this we get a nice solution. This is actually called the exponential growth. Now, although this is very simple, it actually finds its applications. We will talk about it a little bit later. And in some fields, they are sort of trained that when they see an equation like that, they immediately write the solution because they know it, they use it a lot. Okay, how about our money? Well, if our money really is described by this formula, then they should grow exponentially. Does it fit? That's a good question. When people make a mathematical model of some situation, of course they use some insight to form the right formula. But sometimes this is not quite obvious which formula is the best. According to, well, okay, we are making money, so R is positive, so we should expect that our money will behave like this. Does it work? I am not quite sure. So perhaps this model is not exactly faithful. So there are two sides to mathematical modeling. The model, when you solve it and when you analyze it, all this work can be absolutely correct. So the mathematical part can be correct, and mathematics has tools that sort of help you to do correct things, which is nice. But then there is the second question, this one is more important perhaps even, that the model should be faithful. So what people do, they do verification of the model, they look at the predictions, they match them against the data that they have, and sometimes they find out that actually the model is not really very good. For instance, I strongly suspect that wealth of people does not grow exponentially. I think that's too much. So perhaps there should be some other function, perhaps square root of y. Or perhaps some people get even richer, they get rich faster than exponential, then perhaps there should be y squared or some other function. I don't know. So that's something which is out of the realm of mathematics. Somebody has to come up with the right formula to describe the part of the world. So creating mathematical models and verifying mathematical models, that's for specialists. And here we will be interested more in how to handle those resulting models. Okay? This is an exponential growth, a very nice simple model. So let's ask some good questions. For instance, what good is it for? Are there some situations where the change in their quantity is proportional to the quantity? That's a very good question. Actually, there is one such case, and it's very useful and very nice. And it's the spontaneous radioactive decay. The world is composed of atoms, you learned about it at school, and some of those atoms, some elements, they actually decompose, not by our forcing somehow, like in a nuclear power plant or an atomic bomb, but naturally, they sort of feel like it. And this usually happens probabilistically, which means that every atom, once in a while, rolls a die, and if there is a 6 on it, it just decomposes, something like that. So let's say that you have some amount of this material which is decomposing spontaneously, which is decaying happily, and you are interested in the amount, how it changes with time. So y now is the amount of this material. It could be a number of atoms, which would be a very large number, or it could be, let's say, the weight in kilograms. Now, if every atom within a given time span decomposes with the same probability, then how many atoms did decompose? Well, the more atoms you have, the more of them actually decompose. That's a nice direct relationship. If you have twice as many atoms, then within a given time, you have twice as many decompositions, and so on. So this fits the radioactive decomposition really very, very well. Now, radioactive decomposition definitely has R negative. We didn't talk about it too much earlier, but R can be anything in the exponential growth. And in this case, when you have atoms, they decompose, so the number of atoms or the weight of your material decreases, so the derivative should be negative. Here is a positive number, how much you have. I multiply it by a negative number, I get negative derivative. So that's how I see the composition or decrease in the material by taking R negative. How does it look like? Well, we all know how the exponential looks like. Well, where is it? Here. That's the formula. We know how it looks like when R is negative. It looks like this. Here is Y naught. That's where you start. Here is time. And it goes like that. So that's a typical shape for anything which satisfies this condition or this formula with R negative. In particular, carbon. The whole world, including me or you, is composed, among other things, of carbon. It's called C, I think. Now, there is a special version of carbon. The usual carbon is C12, and it's fairly inert. It stays around. But there is a special form which is called C14, and this one is not really happy to be here. So after a while, it decomposes. At the same time, it is also created in the atmosphere by cosmic rays or things like that. It comes from the outer space. So what is happening? We have some C14 in us, and it decomposes, so there is less and less of it. But at the same time, we are getting it in because we are breathing, essentially. So as long as we breathe, there is some balance, some Y naught. That's the amount of C14 that we have in our bodies. Then one day, we die, and we stop breathing because, I mean, most people, when they die, they stop breathing. Zombies don't breathe either, whatever. So we can rely on that fairly well. And once we stop breathing, there is no more C14 coming in. So whatever we had in us starts decomposing like that. So we die, they put us somewhere in the ground, whatever. And 300 years later, somebody digs us out, some archaeologist, most likely. And what they do, they measure how much C14 we have in our body, and they get this. And then they look at the graph, and they say, okay, this is how long we have been dead. Nice, neat. And that's something which is called radiocarbon dating. And that's what they do when they dig out something which is, let's say, 1,000 years old, 2,000 years old, and it must be organic. It must be something which was breathing while it was alive, including trees, lovely flowers, animals, of course, things like that. So that's what archaeologists do. Of course, there is a trouble, because you can see, and we will be talking about this in numerical analysis a lot, there is usually some error over here. When you are measuring how much C14 there is, you don't get a precise number. Your measurement is never precise. And when you translate it into the answer, you get a certain uncertainty. So there is some error in your answer as well. And you can notice that if this thing is really old, and your measurement is here, then the same error over here, I'll mark it so that it looks the same, translates into much bigger error over here. So for older things, the margin of error or the quality of the answer that you get is much lower. And as you keep going into the past, it gets worse and worse, and then it's worthless, essentially. So using this C14 dating, you can get something like, I don't know, 10,000 years, 20,000 years back, which means our hairy forefathers. I mean, not so hairy. They already lived in caves, and they had some tools, Neanderthals and so on. But if you want to see dinosaurs, you're out of luck. So for dating dinosaurs, they use some other elements, not C14. But anyway, this is actually something very useful, which is being used a lot in some fields, and it is all based on a very simple differential equation, exponential growth. And it really, really works well. Let's think of something with R positive. Okay, the money probably doesn't work really that well. I don't see money like that. So is there some other area or some other, let's say, phenomenon which would work like that? Well, let's see. Let's say that you have rabbits. When you have rabbits, they multiply, and common sense says that if you have double the rabbits, then within a certain time, you get double the baby rabbits. And if you have 5 times more rabbits, you have 5 times more baby rabbits, and so on. This seems to work. The amount of rabbits is proportional to the amount of the breeding. And that's something that they use in biology, exponential growth, very popular in biology. This R is then called the breeding constant, for instance. And you get exponential explosion of rabbits. That's something that they actually saw in Australia. When the first rabbits were introduced, I think there was something like 24 of them. And within a few years, there were rabbits everywhere. So this exponential growth, quite good. You can also fit the exponential shape to the number of people on the Earth. When you look at the population growth, up until, let's say, the end of 19th century, this actually fitted quite well, because there is another aspect of mathematical modeling. There are some constants over here. For instance, when you look, well, we don't know how many people there were at the start. Some people think that 1, perhaps, or 2. And I don't want to make fun of it, we simply don't know it. So we have a formula here which has 2 parameters in it. And now we have some hard data. Of course, we don't know how many people there were at time 0, because we don't know what time 0 is. We just have some data. So what we do, we try to choose the parameters so that the curve has the best fit possible. And then based on that, people make predictions. So we should be quite sure that we know what we are doing. Anyway, people tried it with human population. This is called population dynamics. They tried it with rabbits. They tried it with bacteria in a petri dish. If you put some bacteria in a petri dish, let's say doctors do it all the time when they are investigating what people have in their throats or whatever. And the bacteria start multiplying, and they exactly follow the exponential growth. So this is a very good model, but it works only up to some time. It turned out that human beings or bacteria, they all have this property that after a while, the curve starts going differently. What's the problem? Well, the problem is that there is a lack of resources. So we will need a better model when we take into account how many resources we have and so on. But for some parts of development, the exponential growth is actually fairly good, and it has the advantage that it's simple. That's a big advantage of this model. Okay, before we move to something more advanced, something which takes care of this part, let's play a little bit with this model, because this one is quite flexible. We can do some things with it. Here is one. Let's say that we have those rabbits, and let's say that there is lots of area for them and lots of food for them so that they can actually multiply exponentially. But every day we eat 1 rabbit. So there is a constant removal of the population. Why H? H because of harvesting. This is called exponential growth with harvesting. What we get is actually a fairly simple situation, because we can solve it in exactly the same way. So we divide, but now we have to divide by this whole formula. Ry minus h integral dy, and on the right integral, wow, when I divide there will be just 1 dt. Now, do I feel happy about integrating? The answer is not quite, well, it's easy, but I will have to take care of this multiplicative constant. So it's easier if I put it here and also here. And then my situation is quite simple. Now it fits nicely. When you do the substitution, you will see that it will work out really well. So here is the left-hand side integral, and the right-hand side integral. And it looks really, really similar. Okay, I'm going to put the exponential here, then I get rid of the absolute value, and I get Ry minus h is equal to plus minus for the absolute value, e to c times e to rt. I introduce constant d, but perhaps before I do it, I will get rid of this r. So I divide everything by r, and there will be e to c divided by r, and then I introduce a new constant. So let's see, there will be constant d times the exponential. Here will be y, because I divided by r, and I move this one to the right, and I get this. Okay? So we can see that this is actually a shifted exponential. Now, depending on the sign of r, this could be an exponential which goes away from this value, and if r is negative, then it goes towards this value. So all kinds of things are happening. This constant d can be again determined from the initial condition. Well, let's try it just out of curiosity. So let's make a little side note here. What happens when time is 0? When time is 0, then the harvesting amount dividing by the breeding constant plus, and I put 0 here, so plus d should be the initial value. So we look at it and we say, okay, d must be y0 minus h over r. That's the conclusion. So we have a formula. If we know the initial amount, then the development goes like that. Plus y0 minus h over r e to rt for t greater than or equal to 0. So this is what we get with the exponential growth with harvesting. And now we can ask some good questions. Okay, we have rabbits. So rabbits, they are multiplying. So r is positive. Definitely r is positive. What's happening here? Well, h over r is the basic level. Now, if r were negative, then this exponential at infinity would be 0. So the solutions would be going towards this value. But for rabbits, r is positive, so this exponential goes to infinity. It goes away from this value, but it's multiplied by a certain factor here. And there are two possibilities. If this factor is positive, then the solutions just go away. So essentially, we have exponential rabbits in Australia. We start eating rabbits regularly, but they still breed like crazy. They breed like rabbits, let's face it. When does it happen? It happens when this constant is positive. y0 minus h over r should be positive. What does it mean, positive? Well, let's say that it means that h is less than r times y0. How do I translate it back from the mathematical model? So this is the model of Australian rabbits that we use for breakfast, okay? Well, the conclusion, if I translate it back into real life, is that my harvesting was too small. And therefore, those rabbits are still breeding. If the harvesting is stronger, then this constant would become negative, and the population would go like that. It would die out. And finally, there's the value when h is equal to r y0, then this becomes 0, and you simply have a constant number of rabbits. That's the special case. H is equal to r y0. So you can see that the behavior of the system is very, very sensitive to the value of harvesting. I'm not going to talk too much about it because people don't really use the exponential growth with harvesting all that much. As I said, it only works if the population is free to multiply, which in nature does not happen all that often. But it does give us some insight. And this is actually a fairly useful observation that sometimes the differential equation that you have, or the mathematical model, depends on some parameter, and you are perhaps free to influence it somehow. And it may happen that the behavior of the model or the behavior of the solutions depend on the parameter in a nice steady way, sometimes. But it may also happen that the behavior changes abruptly if you change the parameter just by a little tiny bit. Here there is a very tiny difference in age between the exponential growth and between the extinction. Very tiny step. And something like this is called bifurcation, and there is a special theory about it. These systems are very interesting from a mathematical point of view. The behavior is really sensitive. Of course, if you are a biologist, you definitely want to stay in this range. But as I said, this is too simple for such kind of, let's say, reasoning. Okay, let's try another small change of this exponential model. Imagine that you are in the desert. So there is a temperature, let's say, TD, which could be something like 50 centigrades. How much is it in Fahrenheit? 120 something, 122 I think, whatever. Anyway, it's a lot. So you want to feel better, so you take out ice cream from your freezer, let's say mint chocolate chips. That's my favorite. Why mint chocolate chips? Because it tastes great. And second, and that's big advantage of it, if you put it to the freezer, it does not freeze bone hard. It does not become like a stone. So when you take it out of the freezer, it's still a little bit soft and you can immediately start eating. That's what I like about it as well. Anyway, you got your mint chocolate chip. And what's happening, of course, this heat from the desert starts going into it and the temperature starts going up. Let's talk about the temperature and let's call it Y. Why? Because it's traditional in differential equation field. So change in temperature, that's a good question. How is the temperature changing? Well, there is this exchange of heat between the ice cream and the desert, the surrounding desert. Now, the ice cream is too small to cool down the desert, let's face it. So the desert will always be something like 50, let's say, if you do it for 1 hour. Yeah, it doesn't change, so it's 50. But the ice cream will start getting warmer and warmer. Now, this is perhaps not a good ice cream because there would be something like a gradient of temperature. It would be colder inside compared to the outer layer. So let's just say that it's a very flat piece of ice cream. And now we can imagine that the temperature is the same everywhere, okay? My camel sat on it accidentally or something like that. So we have this ice cream where the temperature is the same everywhere and it exchanges heat with the surrounding environment, which is at 50 centigrades. Now, what is the change in temperature? That's a good question, and there is something which is called Newton's law of cooling, I think it is. And it says the transfer of heat between those two environments is proportional to the difference of the temperatures. What's the difference? Well, 50 on the outside and Y on the outside. That's the difference in temperatures. And that's a very nice growth, which is remarkably similar to this one. And again, we can solve it easily. So I'm going to divide. There is this stationary solution business also here. This is actually a stationary solution. And by the way, this equation is autonomous. And when we look at it, we can see that this stationary solution is not stable. Definitely unstable. Okay, let's have a look here. I can see a solution. Y is equal to 50, that's a stationary solution. And otherwise I will just divide and I get dy over 50 minus y is r dt integral logarithm 50 minus y is equal to rt plus c, and I have to be careful because I'm integrating here and there's a minus sign in front of y, so it jumps out like that. You do the substitution if you don't see it. This is basic calculus stuff. Okay, I move minus to the right. I get rid of the absolute value and I get 50 minus y is equal to plus minus e to negative c times e to negative rt. So far so good. I introduce new constant, let's call it d, and then I play with it a little bit and I get that yt is equal to 50 plus d e to minus rt. T non-negative, let's say. And again, I could incorporate the initial value into it somehow. Here is how it looks like. This is the stationary solution 50. And now R is positive because it's a proportional constant for the physics law, for the Newton's law of cooling. Which means this is negative actually. This is an exponential which is disappearing. And it goes like that. Here is my ice cream out of the freezer and the temperature goes like that, exponentially, or like that. If you actually boil the ice cream for some reason, terrible, okay, I'm not going to think about it. So if you boil the ice cream, it will go down with temperature to the nice cool 50 centigrades in the desert. So that's how I see the development. Yeah, again, it's an exponential event. In physics, many laws have a similar shape and then you can expect exponentials. I would say that this is a stable stationary solution or stable equilibrium. And I would be right. we can do the analysis of the slope field here. This is very simple. What's the sign here? Well, it's determined by 50 minus y. If y is more than 50, you get negative sign, decreasing. If y is less than 50, positive sign, increasing. Very nice stationary solution, which is stable. Okay, that's it concerning the exponential growth. I think I milked it enough. Let's pass to something more sophisticated. Here we go. Rabbits. At the start, they can breed freely, and that's the exponential growth. I'm not going to put the constant there yet, but it's the basic reproductive constant R. However, as the population grows, especially here in Europe, where we don't have too much room, there is less room for the rabbits. There is less food for the rabbits. So what's happening is that the reproductive constant actually decreases. That's how we can see mathematically what's happening. They are breeding less fast. Now, again, there's a good question how to describe it mathematically, and there are several interesting candidates, and one of them works like that. The new breeding constant is based on R, which is the basic breeding constant for rabbits that are free to multiply and with lots of food. I divide it by K. What is K? Well, K is something which is called carrying capacity of the environment. Intuitively, I see it as the exact number of rabbits that can live there comfortably, or the amount of food divided by the needs of one rabbit, or something like that. This is simply how many rabbits the environment will be able to support. And, very important factor, K minus Y. So this is the new breeding constant, and it also depends on Y. Let's have a look at it. What's happening here? R over K times K minus Y. Well, there are two interesting situations. The first interesting situation is when the population is very, very small, which essentially means that it's much smaller than the capacity. So let's say that you have Australia, which can support millions of rabbits, but you have just 100 of them. In that case, in this part, Y is negligible compared to K. We can ignore it. And this breeding constant is something like R over K times K, which is R. So at the start, those rabbits or whatever are breeding exponentially. This is just like the exponential growth. This is R. The other interesting situation is when the population is very close to the carrying capacity, or the capacity of the environment. In that case, you get something like R over K times 0. And the breeding constant is 0 and the population stagnates. So these are two very interesting situations. So the population first shoots up very fast, then something happens, because this is getting smaller as the population grows. You can see it here. The bigger Y, the smaller this factor. So the growth slows down, and as the population reaches, if it reaches, we will see it soon, if it reaches the capacity K, it slows down to crawl, this growth. So that's the behavior that I expect. Let's talk a little bit about slope field. That's a good question, essentially. I look at this equation. By the way, there are no restrictions. Nothing wrong with Y, and nothing wrong with, let's say, T for time. So I can handle it as an autonomous equation without any restriction at all. So we have a two-dimensional plane, but actually I restrict myself intentionally to Y non-negative, because we're talking about populations here. Okay, here we go. I'm just looking up here. I can see one stationary solution, which is 0. So we have it already here. And then there's a second stationary solution, which is K. And now what are the signs? Well, up here, when Y is infinity, then this is infinity times negative infinity, negative sign here, and these are positive constants. Okay, let me also remark that R is positive. Okay, so these are positive constants, also K, but that's automatic. Okay, let me write it down. K is also positive. So positive, positive, negative, positive, decreasing. What happens if I'm between 0 and K? If I'm between 0 and K with Y, then this is positive, 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 everything is positive. Which sounds positive. Wonderful. That's the slope field for my equation, which, by the way, is called logistic growth. And I look at it, and I can see that this stationary solution is stable, which is very nice in biology. However, this one is unstable, which means that once you have some population, it will never die out, but it will tend towards this equilibrium, which is actually the capacity of the environment. If you put more population into the environment, let's say that you import rabbits from elsewhere and you overfill the environment, then the population goes down because there's not enough resources, makes sense. And again, it approaches, it seems from the picture, this carrying capacity K. So from the ecological point of view, that's a nice behavior, because the population, no matter what it is, tends to go towards some equilibrium with the environment. Okay, so far our analysis gives us interesting answers. So let's try to solve this equation. That's a very good question. How much room will I need? Okay, here. Is this a separable equation? The answer is yes. I can move y's to the left without any trouble. Let's write it down. dy over dt is r over k, k minus y times y. Okay, stationary solutions. Y is equal to 0, y is equal to k. Otherwise we divide, and we get dy over k minus y times y. So far so good. And I'm also going to move k to the left. And this is r dt. And now we don't integrate. Why? Because, well, we will need to handle this integral. And this area will come handy because partial fractions. Here we go. K over k minus y times y is supposed to be something divided by k minus y plus something divided by y. How did it go in calculus 1? Okay, covering method. I cover y and I put 0 for y, put it here and I get 1. That looks nice. I covered this and the root here is k. So I substitute k over here for y and I get 1. Really? Isn't that nice? So let me see. If I multiply it, y, k minus y cancels, I get k. Yeah, that's correct. That's very nice. Okay, now we can integrate. So I just imagine that this is here, and I integrate. Okay, how do I integrate? This is logarithm, definitely. And this is also logarithm, but there is the minus in front of y, which comes out after I do the substitution. So it looks like that. And on the right, there is RT plus C. Okay. Can we get rid of logarithm? Not yet, because there is 2 of them. And how do we get rid of logarithm? We apply exponential, but to the equation. That's important. I cannot apply exponential here. I have to apply it to the whole left-hand side and to the whole right-hand side. Okay? That's important. And if I apply exponential to the left-hand side, I will have to work it out a little bit more. There will be some 1 or 2 more steps. So I will save some time and do those steps now, just to recall some nice formulas. Logarithm of y over k minus y is equal to RT plus C. And now when I applied exponential to the whole left-hand side, it cancels immediately with logarithm. Yeah, that's nice. And then I get rid of the absolute value, and I get y divided by k minus y is equal to plus minus e to c times e to RT. Okay, now I need to figure out what is y. Okay, y. Y is my target. Y is equal to k minus y times d times e to rt. Okay, what's happening now? I'm going to multiply out the bracket. There will be part without y. This one will stay on the right. And it looks like this. kd e to rt. Now the y part will be moving to the left. I factor out y, and it stays here. And the factor will be divided. So what's the factor? I multiply, I factor out 1 plus d e to rt. T greater than or equal to 0. So that's a formula. And as usual, this expression here can never be 0. So d can never be 0 here in this picture. But if I allow it to be 0, I will get what? I will get 0. And I'm recovering my stationary solution. So that's the usual behavior. However, there is also a second stationary solution. Where is it hidden here? And the answer is it's not there at all. I cannot recover this stationary solution, y is equal to k, from this formula. So that's a new behavior, but we actually, well, I talked about it earlier. When we covered separation, I said, do not rely on your stationary solutions to be always included in the formula. This need not be true. The fact that this 0 were included, you should see it as a bonus. Okay? So if you want to talk about a general solution, we should add this. Or yt is equal to k, t greater than or equal to 0. And now, this is a complete description of the solution. Okay, let me put t here. And you could call this a general solution if you want. What can I expect from this? Well, we can all visualize the stationary solution k. It's a constant function, but how about this one? E to rt. R is positive. Yeah, it's written there. R is positive, so that's an exponential, it goes up. I multiply by constant, which, well, it could be negative, and then I mix it up. Can I visualize it? The answer is, I guess I'm not experienced enough. Now, we will soon ask Maple about a picture, so that we can have some idea how these solutions look like. Of course, we do have some idea from the slope field that we sketched before. So, just out of curiosity, let's confirm something. I look at this formula and I say, okay, what happens if we send time to infinity? Well, for this version, it's obvious. The limit is k. How about this version? Well, when time goes to infinity, r is positive. Positive number times infinity is infinity. E to infinity is infinity. So I can see two infinities here, and they dominate. Compared to one, they win. Okay? So, well, unless d is 0, that's a special case. When y is 0, the limit is 0. So let's talk about positive d's or negative d's, non-zero d's. And then this dominates, and I could use some cancelling, for instance, to see the outcome. That would be a good idea. So I'm going to cancel or divide both numerator and the denominator by the term which I feel is dominant. That's what I learned in calculus. The dominant term exponential, I divide, and it becomes this. kd on the top, e to negative rt plus d in the denominator. How much is it? Well, negative r is a negative constant times infinity is negative infinity. This goes to 0, this exponential thing. And because it goes to 0, the outcome is kd divided by d, which is k. And as I said, this is true whenever d is different from 0. That's important to notice. So, here is the conclusion. We have one exceptional solution, which is the 0 solution. This is the unstable equilibrium. But as soon as some solution is away from 0, which means d is non-negative, then all the solutions at infinity tend to k. So this picture sort of seems to be confirmed. Okay? Let's see what Maple thinks about it. I have a picture here ready for you. This is the actual slope field, not just a sketch, but the actual slope field. We can see the directions, the arrows, they flow nicely. And there are some blue curves. And let's say the second one from the bottom. You can see the exponential growth at first. That's the exponential. And then it levels off towards this equilibrium k. If the initial population is too large, which is the top curve, it decreases, and again it goes to this carrying capacity of the environment. So this all works out very nicely. So that's the logistic growth. Now you may feel that we had enough population ecology or population dynamics, so let's talk about something else. The logistic growth is actually used in medical field because it describes rather well the growth of tumors or cancer, which is fairly important because when they try to cure cancer, they are essentially killing it by giving the patient poison. And the trick is you want to kill the cancer without killing the patient. That would be nice. So the more they know about the growth of the tumor, the better they can judge the doses for the poison. And quite recently, accidentally, I stumbled upon an interesting article by some physicists, by some medical people from research, and they were comparing 7 different mathematical models of tumor growth. One of them was actually the logistic growth. So this is really used by medical profession, and they actually compared the data which they had on the tumor growth, on the actual situation, and they compared it with what the mathematical models, the 7 models, were actually predicting or showing. And they had some interesting conclusions. So for instance, depending on the kind of the tumor, of the type, different mathematical models turn out to be slightly better, which is interesting. But what was perhaps the most interesting part for me, that in some situations, for some tumors, actually it's not quite clear which model is the best one. So there are several candidates, and based on real-life data, you cannot really distinguish which one of them is the right one. And that's a problem, because you have some data, and I have 2 competing models, and they sort of look both similar to the data here. And you want to make a prediction, and those 2 models, they do that. And that's very unpleasant. Modeling real-life phenomena can be very, very difficult, and therefore predictions can be difficult. You probably notice that there are lots of predictions about economy, about things like that, and very often they are wrong. Well, that's because it's not quite obvious which model is correct. Economy is a prime example because economy deals with people, and people are really difficult to model mathematically. Why? Because they don't follow rules. They do whatever they feel like, and people are bad for mathematics. I mean, as objects, mathematicians are fine. So that's an interesting thing. So logistic growth, medicine, tumors, things like that, very useful. And talking about economics, actually people in economy field, they actually use logistic growth to simulate, how would I say it, the spread of innovation in society, which is interesting. I didn't know about it. Again, accidentally I found out. So the logistic growth, although it looks also very simple, it can be quite useful, and actually it's quite faithful. Human population actually follows logistic growth quite well. That's a good balance, because if you want to make a model more precise, it becomes more complicated, and then you cannot solve it, and you cannot analyze it perhaps that well. So that's a fine balance. People tried different ideas how to change this breeding constant based on the population. So there are some competitors, and they have some advantages, disadvantages, but the better you want to have it, the lower the chance that you will be able to handle it, actually. So yeah, that's pretty sad. Okay, that's the logistic growth. Let's play a little bit. We now know that the logistic growth is a much better model for population because it takes into account limited resources. What if somebody comes in and start messing up with the population by taking away a constant chunk of it? So this will be the logistic growth with harvesting. Y prime is equal to R over K, K minus Y, times Y, minus the harvesting, constant harvesting. That's a model which is of special interest to marine biologists. They also use differential equations. We have some fish population, let's say cod, or tuna, or whatever. And if there were no humans, they would breed according to this. Well, perhaps quite not, because they're predators. If you want to put predators in the picture, we need another variable for the predator population. We are not ready for systems with more unknown functions. But we will in a few lectures, well, in a few months, okay? And then we will return to this. Very nice. But just one population. If you leave it alone, it's essentially a logistic growth. But here come the people. And the question is, what will it do with the population? We definitely do not want to destroy the cod population, because then there will be no more cod to eat. Yeah. Here we go. How does it behave? That's a good question. I could try to solve it by integrating, but you can notice that using partial fractions here would be really, really hard. I mean, not hard, but messy. It gets ugly, because we would have to somehow handle the quadratic polynomial. Not very nice. Let's have a look at it. What kind of quadratic polynomial is it? I guess I can factor r over k. And what we are left with is minus y squared plus capital Ky. So far, so good. And I've been factoring r over k, so there must be minus hk over r. So if I want to integrate, I would have to take this quadratic polynomial and somehow handle it, which is not very easy. The formulas would be real ugly. So instead, let me try just a sketch of the slope field. Okay, I'm inquiring about the sign of this thing. R is positive, k is positive. So I just inquire about this quadratic polynomial. Okay, how about the roots? That's a good question. Okay, let's put it here. How about the roots? Y is equal to, why not, let's say, because these will be the stationary points. Stationary solutions or equilibria. Quadratic formula, most likely. Okay, here we go. Minus k plus or minus square root k squared minus 4 minus 1 makes it into plus, minus makes it into, okay, minus 4 hk over r. Did I make a mistake somewhere, anywhere? Nope, I don't think so. Divided by 2a, which is minus 2. Can I make it somehow nicer? That's a good question. I look at it and I don't feel that it can be improved much. Okay, here we go. Minus minus. So it's k over 2. That's the basic level for my two stationary solutions, or for my two equilibria, if there are any. Then there will be minus plus square root. And now I'm dividing by 2. I put it under the square root and becomes 4. And it's k squared over 4 minus hk over r. Okay. Equilibria. Do they really exist? That's a good question. It all depends on this discriminant, they call it. I learned this in elementary school, so I forgot. I just know how to use it. I don't know the names. So this thingy over here should be preferably positive. If it's positive, then I get two stationary solutions, two equilibria, and I know how to handle this. This will split into factors. Okay, what's the condition? Okay, the condition will be here. K squared over 4 minus hk over r should be positive. So I'm going to multiply everything by 4, I'm going to multiply everything by r, and divide by k. And when I do it, I get k r should be larger than, and I was multiplying by 4 and multiplying by r and dividing by, so it's 4h. That's it. So my condition is that h should be less than 1 over 4 kr. That's the condition which bounds the harvesting from the top. It says the harvesting shouldn't be too much. Okay, here we go. First situation, h is less than 1/4 kr. How will it look like? Well, here we go. two stationary solutions. Notice that k over 2, if you square it, you get k squared over 4, and then there is the square root. So without this term, these two would be the same. But I'm actually making it smaller. So I have k over 2, and then I'm subtracting and adding something which is smaller than k over 2. So k over 2 is somewhere here, and I move it down and up by some amount, which is not reaching all the way down below the x-axis. It stays here, and it stays here. That's the two stationary solutions. Let's say with a tilde and with a hat. Okay? This one has a plus, and this one has a minus. Two stationary solutions. And now I'm going to imagine that I factored this out into two factors. That's what happens here. It becomes like that. And there is a minus in front of y squared, so this is a parabola which goes like that. So when you think about it, it doesn't take too much effort to see that when y is infinity, this will be negative infinity, and I get a decreasing picture. Here, increasing. Here, decreasing. So this is actually a stable equilibrium, and this is unstable. So what does it tell us? This tells us a story which actually is quite reasonable when you think about it. If the harvesting is not overdone, if I harvest reasonably, if I am not too greedy, then the fish population will be stable within some limit. I shouldn't, well, if the population is too small, then it will simply die out with harvesting. Okay, but if I can keep the fish population at a certain level, then it will be stable. It will tend to go towards this upper equilibrium, which is a good situation. Okay? How much harvesting can I do? Well, it depends on the carrying capacity of the environment and on the breeding constant of the fish. The more the fish multiply, the more can I actually take away from the population. So this all seems to fit. Okay? What happens if I start increasing the harvesting? What happens when h gets larger and larger and larger and larger? Well, I will be making this number larger, so this whole number, because I'm subtracting, will be smaller. It will be getting closer to 0. These two equilibria will be getting closer and closer to k over 2. So the safety strip, this is a safety strip. If I keep population here, it's safe. The safety strip will be getting more and more narrow. There will be a very narrow band here of increase and decrease up here, but this one is okay. It simply still means that the population goes towards this equilibrium. But this strip will be getting wider and wider. I would have to be more and more careful about not actually killing out those fish. So by increasing the harvesting, the situation is becoming more volatile. I have to be more careful, more dangerous. Of course, what happens when h is equal to 1/4 kr? That's the key question, because that's where things get really interesting. And the answer is, well, there will be just one equilibrium, namely k over 2, because then this square root will be 0. Just one equilibrium. Now, what happens with the sign? When I have a multiple root, it means I can complete a square. I factor out minus and I complete a square, so it will be minus something squared. That's how it looks like. Minus something squared. The sign is negative and negative. This is a very dangerous situation. If the population is large enough, it will go towards k over 2, but if by some accident, and something may happen, a volcano blows up or something, the population drops below k over 2, it dies out. And it will be close to k over 2 because it will be approaching k over 2. So this is a very, very tricky situation. You start with some population and you start harvesting at some rate, and the population goes here, whether you like it or not. And then this is a very sensitive, very vulnerable. Whatever small problem happens, the population goes down. This is very bad. So you definitely do not want to see that. Well, what's the last possibility? When you harvest too much. When you harvest too much, then there are no real roots. So this will be a quadratic factor which does not have a root, and there is minus in front of y squared, so the graph looks like this. This is always negative. And the picture looks like that. So no matter what you do, the population dies out, which is common sense. If you harvest too much, you simply eat it all. Okay, so that's an interesting use of logistic growth with harvesting. You can play with it like that. You can make little analysis. What people do in marine biology, they're actually trying to determine reasonable amounts of harvesting which they can allow people to do. And then you have some limits for the fishermen and things like that. This is actually all based on mathematical modeling, I learned. Okay. So much for the logistic growth. With harvesting, let me just show you a few pictures. What I did over here is I took a certain K and a certain initial value, Y naught. I start from a certain population of fish. So you can see the environmental limit, that's the red curve. I start at with some population, and then I tried different harvesting levels. And you can see that for small harvesting, the population went up, sometimes quickly, sometimes slowly to this level, this carrying capacity. But if I overcooked it with harvesting, the population dies out. Okay? So that's the outcome of compute trying to solve this differential equation. And that's it for the logistic growth. Let's see what's next. Now we will look at an example from physics. Imagine a bathtub. And there is some water in it, which does happen sometimes. Namely, there is V0 liters, so that's the volume, at time 0. Also, at time 0, we do something, we pull the plug. And as you can expect, the water starts pouring out and the volume will be changing, namely decreasing. But I do not know yet officially. So we will see. What's the volume doing? Depending on time. That's our question. Well, to answer this question, we have to investigate what's happening within short time intervals. So we'll look at specific times and ask a good question. What's happening there? And we see that if we fix some time interval of length, let's say delta t, a short time interval, then within this time interval, the water will pour out and form a shape. It will form a tube, or perhaps a tiny cylinder if you want. And the volume of this water in this cylinder or in this tube actually tells us by how much the overall volume decreased. So the change in volume, delta V, will be negative because it's decrease. Okay, what's the volume of this shape? Well, we know the area of the base, because that's the area of the hole. We can measure it. Let's call it little a. And this, the base, has to be multiplied by the length of the tube. Now, what is the length of the tube? Well, let's imagine how it goes. At a specific time, we start our stopwatch, and there are some molecules here at the hole. And they start flowing, and when we stop the stopwatch, the time delta t is over, they are just here at the end. So the length of the tube is exactly the displacement or the distance which was covered by the molecule of the water. Now it has a certain specific velocity as it goes through the hole, let's call it v, and then it runs with this velocity for time delta t. And that's our formula. Very nice. Now we divide by delta t. Which gets us to the position when we start arguing that delta t should be actually very small. Because if it's a little bit longer, then this tube is longer, and as the molecule goes down, gravity is acting on it and increasing the velocity v. So it would not be constant anymore, it would change, and that would make our formula much more complicated. We do not want that. So we are considering just very, very tiny time intervals. In fact, the best time interval is the one which is the shortest possible, which is dt. So from delta, we will pass to d, differential, infinitesimal, and dv over dt, that's actually the derivative. Very nice. That's the beginning of a differential equation. Unfortunately, there is dv at the end, which we don't like. That's a new variable, we don't want to see that. Okay. So we go to physicists and we ask them, okay, what's the water? What's the velocity of the water flowing out of the bathtub? And they tell us, well, there is something which is called Toricelliho law. And Toricelliho law says that the velocity is proportional, directly proportional. So there's some constant to square root of the pressure. And this constant, it incorporates many things like the shape of the hole, the viscosity of the water, things like that. Because it need not be a water. Let's say you have a bathtub of jelly. Or, well, that wouldn't work too well. Water. Let's make it water. When I was at elementary school, they taught me that the pressure, which is here, is caused by the water column which is above it. So this height is very important. And the formula actually reads, here's the C, the pressure, the hydrostatic pressure, is the density times gravity times h, which is the distance between the hole and the water level. So far so good. Constant, constant, constant. We can pull them all together, lump them into one constant c tilde, and then the square root of h. So we moved from velocity to something else, but we are still not happy because h is not in our differential equation. But when we talk about h, we are really close to volume because they are related. You can calculate the volume and as it depends on the height, on the water level. Or vice versa, that would be nice. Unfortunately, it's not easy for a bathtub because it's sort of roundish. The shape is very complicated. Here is an assumption. We will assume that our bathtub actually has vertical sides. And then there is some bottom, which has known area A. We can measure it again. Now, that's not a typical bathtub, so let's speak about something else instead. It could be a barrel. Barrel is round, it has flat sides, it has a bottom, yeah? Or it could be fishbowl, rectangular box, fishbowl. Yeah, you can buy fishbowls like that. Anyway, here is the water level, here is the depth, and there is a very nice formula then. Volume is the area times the depth. Very simple. And from here, depth is 1 over A times the volume. And we can substitute it into this formula. 1 over A appears here, and I connect it with my constant. So yet another constant, C hat, square root, volume. And that's how we like it. That's a nice formula for velocity because we can merge it with this equation. And we get that V prime is minus, okay, there will be A, and there will be C hat, so that's a new constant, let's call it K. Minus K square root of V. Very nice autonomous equation. Definitely separable. And just out of curiosity, K is positive. This may come handy. Can we solve it? Definitely. Let's have a look at it. dv over dt is negative k square root of v. Well, we want to divide by the square root, and we know, because we've been trained to think about it, that we should worry about the division by 0, and we get a stationary solution. Okay, so that's out of the way. And we can move to the second case, when v is not 0. Okay, dt to the right, square root to the left. dv over square root of v is minus k dt. We attach the integrals. And we integrate happily. 2 square roots of v is minus kt plus c. Then I divide by 2. Square root of v is minus 1/2 kt plus 1/2 c. I don't like that. Okay, so this will be c tilde and this will be c. Okay, c is 1/2 of c tilde. It looks much better. And finally, v, as it depends on time, is c minus 1/2 kt, that all squared. That looks good. Let's think about it. That's a parabola. It's a nicely shaped parabola because it's just some bracket squared. So it's negative, but it touches the x-axis. It can be 0. Where? Well, let's have a look at it. When is this 0? It's 2c divided by k. And here is our parabola. That's assumed to be a solution. But that's strange, isn't it? Let's see. I have some volume, V0. I pull the plug. The water starts flowing out, so I have less and less water in my bathtub. Then it's empty, and then it starts filling up again. This is weird. And one should ask, okay, what's wrong here? That's a very natural question at this moment. Well, there are two possibilities. One possibility is that all the work was mathematically correct, but the model wasn't really all that good. This can happen sometimes. And then we just take away from the model things which are applicable and we ignore the rest. However, here we actually made a mistake in mathematics. But it is a mistake which is in a way hidden from us because we never saw it before. When we do equations at school, they are usually nice. And also when we do equations in applications, they're usually also nice. There are two things happening here which are not typical, which are special. And if you are not aware of them, if you are not ready for them, it's easy to overlook them. When we are in doubt whether something is a solution, we can always check. So let's check. I take this formula, I substitute it on the left. I'm supposed to take the derivative. So it's twice c minus 1/2 kt times, and now we have to multiply by the derivative of the inside function. So it will be minus 1/2 k. And what we get, okay, 2 cancels, it will be minus k, c minus 1/2 kt. That's the left-hand side. Now let's have a look at the right-hand side. We see minus k. That looks promising, definitely. And then there is a square root of v. We should take square root of something squared. Square root and square, do they cancel? The answer is unfortunately not. They create an absolute value. And when we compare, we can see that these two are not the same in general. So this formula actually does provide us with a solution as long as these two expressions agree, which means this expression should be non-negative. And then we do have a solution. This is really tricky. This is mean, even. Treacherous. Can I somehow see it? Perhaps I overlooked something. Well, how do we determine the region of validity? Usually we do it like that. We look at the equation and we ask, is there any restriction? And of course I can see one. V should be greater than or equal to 0. That's a definite restriction. Yeah, that's true. For any t, I could put t belonging to R and it will still work. Okay, so far so good. What do we do next? Well, we look at the answer and we ask, is there something wrong? And the answer is no. So that's what we normally do. But in fact, we should also scan the procedure for restrictions. And as we are scanning it, we can notice that square root of v, that's a non-negative number. This expression should not be allowed to be negative. Minus 1/2 kt plus c must be greater than or equal to 0. And that's another condition that we overlooked. But it's hidden there. This is really devious. Okay, I move it to the right. T should be less than or equal to c over k. We saw that before. That's the vertex. So those two conditions, they're actually telling us that our solution is only good here, up to this point. It's not good here on the right, unfortunately. Well, that's life. I talked about two problems here. That's just the first one. We overlooked one condition. There is a second problem. I talked about it in previous lecture on analyzing solutions, the section about Picard's theorem. We have two branches here. When v is 0, we get a stationary solution. When v is not 0, we get another solution. But it may also happen that there is a solution which is sometimes not zero and sometimes it is zero. Well, actually, that's the one. This solution is sometimes, namely over here, equal to zero. So the two families of solutions, they actually meet. Again, that's something that we normally do not see, but here it happened. And we have to know what's going to happen next. What's the reaction to such a situation? Well, we should inquire about the nature of this meeting. There are essentially two different situations. One situation is that you have one solution and another solution, and they meet like that. And if this happens, then you don't have to worry, because each solution simply goes its own way. So that's a nice case. If something like that happens, you don't have to worry, no extra work needed. However, it's also possible for one solution to go like that, and another solution to go like that. Or perhaps you have one solution like that, and another like that. And when this happens, then you're actually allowed to jump from one solution to another. Okay, they should merge here. They should go through the same point. So you could start here, and you can here choose which way, in which way you can continue. And the same here. You start, and here you can choose the branch. And this is what's called gluing solutions. You have segments of solutions, and you can glue them together in any way you want. How do you recognize these two cases? Well, you inquire about the slope of the two solutions at the meeting point. If the slope is different, you don't have to worry. If the slope is the same, you do have to worry. Okay, we have our parabola here. And we have the stationary solution. They meet here. What are the slopes there? Well, the stationary solution has slope 0, that's obvious. And the parabola, if you differentiate and so on, it also has a slope 0. So that's the meeting place of two different solutions. And therefore, we can glue them together. This solution comes here and stops, but we can glue it with the stationary solution, and it actually goes on like that. And it's mathematically correct, and it also makes sense from the physics point of view, or the bathtub point of view. So that's very nice. So how would I write my solutions? Vt is, well, first of all, I can follow, if I want, the parabolic part. Well, actually, since I'm writing it now, may I introduce V0? That's a good question. Yes, let's introduce initial condition. So let's introduce it here. If I know that at time 0, the volume should be V0, how does it work? Well, the volume should be when time is 0. This should be V0. C is square root of V0. That was easy. So that's one possible formula that we can follow, but we can only follow it down to this vertex. So t belongs to interval 0, and it's 2c, yes, 2c. 2 square roots of V0 divided by k. And then we switch to the other solution. And then there is the second possibility that we simply take the stationary solution. But it is actually included, because by changing c, we can change the position of the vertex, and if we put it here, we are simply following the stationary solution. If we put 0 for the initial volume, then this number will be 0, this number will be 0. So this part will be non-existent, going from 0 to 0, and then go from 0 using the stationary solution. So we were lucky, and the stationary solution as itself actually got included in this formula. However, that's only because we decided to start our exploration at time 0. Notice that if we were just mathematicians, if we didn't know anything about applications, somebody just gave us this equation, then we would actually have to include two types of solutions. This would be one where we would have parabolas going all the way to infinity with any position, and then we would continue using the stationary solution. So that would be one family, and the second family would be the stationary solution. Now this cannot be obtained by starting with parabola, because we go all the way to negative infinity with time as a mathematical solution. Okay, so that was interesting. There are some really devious things happening with such a simple differential equation. By the way, this model is quite good for water, definitely, and you can try it at home. You need a rectangular fishbowl. Fishbowl is a good thing. Rectangular fishbowl, it has to be transparent. You've got some water here. You drill a small hole here, but you plug it momentarily, and you draw lines here which should be regularly spaced. Let's say 1 centimeter apart or something like that. And then you take your watch, and when the time is, let's say, 0 somewhere, you pull away the plug and you put a dot here. You wait 1 minute, the water level will go down, and you mark the new water level by a dot here. You wait another minute, water goes down, and you mark the water level here. And you keep doing like that. You keep marking the water level, going from line to line. And what you should get is essentially the shape of a parabola. Actually, the shape here will not be quite precise, because when there is just a little bit of water in your fishbowl, then there will be some other phenomena from physics entering the play. So the Toricelliho law does not follow quite precisely anymore. Things will get complicated. But if you ignore this part, and if you look at the part where there was quite a bit of water, then you should really get a nice parabolic shape. So that's the bathtub problem, or the Toricelliho law problem, if you want. A very nice differential equation with some surprises. Okay, let's go for our last example. We started this chapter on differential equations with an example of a free fall as an inspiration. And it was a very simple example. But we have learned some things since then, and let's have a look at a more sophisticated version. We start by introducing y-axis, which actually points upwards. That's how we measure elevation. There's an object here. We release it, or we flip it in some way, and it starts behaving according to the gravity law. And we had a formula for that. That's how we started this chapter. But this time, the elevation is measured in the opposite direction, so we have to put the minus sign here. The elevation goes up, and therefore the acceleration also goes up, but the gravity pulls down. Makes sense. To make it even better, we are going to ask, what are the major influences? And the major influences are the gravity, but also the air resistance. As long as the object is slow, then perhaps this formula would work quite well. But once it picks up speed, we have to really worry about the air resistance. We have to ask physicists, and they tell us, well, the air resistance is proportional, directly proportional, to the square of velocity. This proportional constant, it hides many things. The density of the air, the shape of the object, the cross-section of the object, these are the major factors. What is the sign here? That's a good question. The air resistance, or the drag, always goes against the movement. So the sign here can actually be plus or minus, depending on what the object is doing. If we flip it up, it keeps going up for a while, and then it goes down. So right here, at the highest point, our differential equation would have to flip the sign, which is very unpleasant. How do we do it mathematically? It's not possible. We would have to solve it as two separate problems, which can be done, but it's complicated. So I'm going to make an assumption. I'm going to make the assumption that the derivative is negative. What does it mean? Well, it means that it goes down. So we are just releasing, or perhaps flipping down, some objects. These are the trajectories that we are interested in. And then we can simply put plus here, because if those objects are falling down, then the air resistance pushes them up. That's the basic differential equation, and it's a second-order differential equation, so separation doesn't work for it. We will learn how to solve some higher-order differential equations later on, but this one is not of the right type. So in this course, we will not learn how to handle it, so that's a good one. It's one of those really good ones. And people who worry about free fall with air resistance, like people in NASA who have to put things up or catch them when they go down, they have to solve things like that numerically using computers. And we will have a little lecture on how to solve equations of higher order numerically. So we will see examples like that later on as well. For now, why am I showing this example now when we don't really know much yet? Well, here is a little trick. Notice that there is no y in this equation, so I can use substitution. I take y prime and I hide it as v. What is v? Well, that's the velocity actually. Now the calculations in this example are not going to be exactly friendly, and I will be using tricks to make them a little bit more palatable. And here comes the first one. When I talk about velocity of an object which falls down, I'm naturally thinking of the downward direction. So that's what I'm going to do. I'm going to put minus sign here to reverse the direction for the velocity. And now let's substitute. Y double prime is actually minus v prime. And on the right we have minus g plus k v squared. And that's a first order differential equation. Let's play with it a little bit. V prime is equal to g minus kv squared. And one more change. I'm going to integrate soon. How do I know? Well, there is no t or no x on the right. This is an autonomous equation, which is automatically separable. I can take this whole factor and divide, and all the v's will be on the left. So in order to make my life easier, I'm going to remove the factor in front of the variable, because for integration, this causes sometimes complications. So here is the form that I really want to see. When I factor out k, there will be g over k here, minus v squared. And now I look at it and I say, okay, that looks like a nice separable equation. Let's play. Okay, first I noticed that I can make the right-hand side 0 by a smart choice of v, so there are some stationary solutions. Vt is equal to plus or minus square root of g over k. T greater than or equal to 0. Very nice. Okay, let's move on. If v is not plus or minus square root of g over k, then we can do the separation, and we get dv over. Okay, I'm going to keep k on the right, so on the left there will be just g over k minus v squared integral, and on the right there will be this k dt, and that's about it. Okay, I would like to factor out, I know the roots here, because I have to use partial fractions decomposition. That's a polynomial of degree 2. Okay, that's life. How will I play it? How will I play it? Okay, I will do several tricks. One trick is that I multiply both the left and the right hand side by minus, so that v has a positive sign in front of it. I like it that way. And the second trick I'm going to do, I will introduce a for the square root of g over k. That's a fairly convenient notation, obviously, here. So, how will it go? There will be dv, there will be v square minus a square on the left, definitely. And then there will be integral minus k dt. That looks fairly nice. Okay, now the partial fractions decomposition. V minus a, v plus a in the denominator, minus integral k dt. Now I left some room here because I will do another trick. I have been doing this partial fractions decomposition a lot in my calculus course, and students as well, and we have some experience with how this will go. So I know from experience that it would be really nice to have 2a here. And if I want to have it here, I also have to have it over here. Okay? Let's play. Now I do the partial fractions. V minus a, v plus a, dv should be, and let's play here, this is minus 2, and a is actually the square root of g over k, so k's can be put together. This is square root of gk times t plus c. So far so good. Okay, on the left. Here, the number on the top is obtained by covering up this, and here I substitute the root of this, which is a. So I'm substituting a, 2a, it's 1. See, that's how nice it is. Okay, let's play here. I cover up, the root is minus a. Minus, 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 it's negative 1. Here we go. let's move on. This looks like a calculus review. Logarithm of v minus a minus logarithm of v plus a is equal to minus 2 square root gk times t plus c. Does it look familiar? The right hand side looks good. Okay, let's move here. Okay. Logarithm of v minus a divided by v plus a should be minus 2 square roots and so on. So far so good. Now I apply exponential to each side and I do the plus minus trick. Plus minus trick, exponential and exponential. Okay. Now we will introduce constant d, which right at this moment should not be 0. And we have to isolate v from here. So I'm going to multiply out. Perhaps I can introduce another symbol here so they don't have to copy it all the time. Okay, v is on the left. There is one v from here, and after I multiply, I will move this to the left. A is on the right. A from here, A from here. These two look remarkably similar, and that's as it should be. So I think it's hopeful. And I think we are ready to write the answer. So I'm going to replace a with its original meaning. Square root g over k times fraction 1 plus d e2 negative 2 square root gkt divided by 1 minus d e2 negative 2 square root gk times t, where t is greater than or equal to 0. Okay, let's see. What happens if I put 0 for d? That's a good question. If I put 0 for d, then this disappears. 1 here, square root of g over k. I'm getting one of these stationary solutions, which is nice, not the other one. Yeah, that's interesting. But anyway, I don't really care about the other one. Why? Well, because, here we go. One stationary solution, another stationary solution. So these are actually equilibria. But we are only interested in the cases when the stone falls down. We are never interested in negative velocities. So this is really not relevant. So I'm really interested only in this upper part. Let's have a look at the formula here. Let's say differential equation which is autonomous. Let's talk about slope field. When v is really large, close to infinity, then this will be negative infinity, negative derivative. So it means decreasing velocity. Here, positive. I can imagine that velocity is about 0. And when velocity is about 0, then the derivative, I can see it here perhaps better, then the derivative is positive. Okay. One could play also with things down here, but we are not interested in them anyway because they are not relevant. This looks like a stable stationary solution or stable equilibrium. Is it borne out by our solution? Well, let's have a look at it. What's the limit of the velocity as t goes to infinity? Well, if t goes to infinity, that's a positive constant. Times infinity is plus infinity, but there is minus in front of it. Exponential to negative infinity goes to 0. 0 here, and we get this. This is so-called terminal velocity. By the way, we have an analytic solution for this differential equation, which means we have an analytic formula for the velocity. If we have a formula for velocity, we can recover the position by integrating. Well, just look at it. Good luck integrating. Try it. It's not pleasant. Okay, here we go. Terminal velocity is very important. That's the moment when you have a velocity so that the force of gravity and the force of drag of air resistance are exactly negated. So once you reach this, you stay like that. If I remember correctly from what I read, it takes about 1 or 2 minutes for a human being to reach this terminal velocity, and it's about 200 kilometers per hour, which is rather a lot. It depends on your shape and other things. There have been people who actually had to experience this because, let's say, they were skydiving and their parachutes didn't deploy, things like that, or during the war when the airplane was shot up and they just fell off the airplane without parachute. There are cases like that. So it's really good to know your differential equations, because the good news is it takes several minutes to actually reach the ground if you start, let's say, at 2,000–3,000 meters. So you have lots of time, and you have a time to write down the differential equation, you solve it, you find a formula for the terminal velocity, and you start thinking, okay, I'm up there, the Earth is getting nearer and nearer. I want the terminal velocity to be as small as possible. What can I do about it? Well, gravity. Can I make the gravity smaller? Probably not. Okay, another try. Can I make K larger? I want K large. Well, that's the air resistance built into it. So the cross-section and the shape. So what you want to do, you want to spread as much as possible. You spread your shirt, you spread your jacket, you spread your ears. If you have hair, it's a good idea to let it out. You make a shape which is not very aerodynamic, and then you need a lot of luck. And some people had lots of luck, and they probably also knew differential equations, and they actually walked away from a situation like that, which is a good news. And that's a fitting end to this chapter on applications of differential equations of order 1. They can be useful.